Bismillahirrahmanirrahim. Dear students, this is lecture number 61 and class first year class grade 11 and chapter is solutions and 10th chapter Rod's law grade 11. Very important topic, Rod's law. French chemist Rhodes discovered the quantitative relationship between vapor pressure of solution and concentration of solution. Vapor pressure means pressure exerted by the vapors of liquid at equilibrium. Concentration, number of moles of solute present in 1 deciliter. So, quantitative relationship between vapor pressure of solution and concentration of solution. This relationship is called Rod's law. There are 3 ways to define Rod's law. Number 1. 3 ways to define. When a non-volatile and non-electrolyte. Non-volatile means which is not going to evaporate at room temperature, salts, sugar, glucose, urea. Non-electrolyte dissolved in water which is not going to conduct electric current. It states that non-volatile solute is dissolved in a solvent. The vapor pressure of solution P is a capital P is a vapor pressure of solution, means you put the solute in a solvent to make a solution. Non-volatile solute is dissolved in a solvent. The vapor pressure of solution P is directly proportional to the mole fraction of solvent X1. X1 is a mole fraction of solvent. Mole fraction of solvent means vapor pressure of solution directly proportional to the mole fraction of solvent, or P is directly proportional P naught X1, where the P naught is a constant proportionality. This is the constant and it is a vapor pressure of pure solvent. Water like this one, pure solvent. It is a vapor pressure of pure solvent. So P is equal to P naught X1. A more common form of the Rod's law is obtained by simple. We have binary solutions. You know that X1 is a mole fraction of solvent, X2 is a mole fraction of solute, always is equal to 1. This will be always is equal to 1. So when we are going to calculate the X1, so X1 will be is equal to 1 minus X2. X1 is equal to 1 minus X2, then put value here. So P is equal to P naught. X1 is value for this one. So this is a P naught and 1 minus X2. So P will be is equal to P naught minus P naught X2. This is equation number 2 and this is equation number 3. P is equal to P naught minus P naught x2. So P naught is the vapor pressure of pure solvent greater than the P, which is the vapor pressure of the solute, and solvent to make a solution, vapor pressure is going to decrease. That's why P naught minus P naught minus P will be is equal to P naught x2, or delta P will be is equal to P naught x2. So delta P is equal to P naught x2, or P naught minus P naught is the vapor pressure of pure solvent which is greater than the vapor pressure of solution. So P naught and P is called lowering in vapor pressure of solvent. Delta P or P naught minus P is lowering of vapor pressure of solvent. Lowering of vapor pressure of solvent. Rolle's law is P, vapor pressure of the solution, directly proportional to the mole fraction of solvent x1. P is equal to P naught x1. P naught is a constant, proportionality constant. It is the vapor pressure of pure solvent. It is a constant. So for the binary solutions, x1 mole fraction of solvent, x2 mole fraction of solute must be equal to 1. We done the numerical before. So realize this, x1 is equal to 1 minus x2. Put in this formula, P will be equal to P naught in bracket 1 minus x2. Solve it. P multiply by this, you will get P naught and minus x2. Rearranging this, so P naught minus P is equal to P naught x2. This is called delta P. So this delta P or P naught minus P is equal to lowering of the vapor pressure of the solvent when you put the solute. Its vapor pressure will be lowered. So this is the first definition, and there is another second definition also. You can define the Rolle's law also in this form. You can define Rolle's law in this form. Therefore, Rolle's law can also be stated as a lowering in vapor pressure. That's why I told you P naught minus P or delta P is directly proportional to the mole fraction of solute. Mole fraction of solute. So by rearranging the equation, you will get P naught minus P divided by P naught is equal to x2. Second definition. Lowering in vapor pressure is directly proportional to the mole fraction of solute. So we get this equation. So this P naught minus P is equal to delta P divided by P naught is equal to x2. So dear students, there is another also. This delta P over P naught or P naught minus P over P naught is a relative lowering in vapor pressure of the solvent. Relative lowering in vapor pressure of the solvent. So there is a third definition of the Rolle's law. Stated that relative lowering in vapor pressure is equal to mole fraction of the solute. Mole fraction of solute. So lowering in vapor pressure depends upon temperature, whereas a relative lowering in vapor pressure is independent of the temperature. This is a Rolle's law. Three definitions I told you. This is the second definition. And third definition, I told you that lowering in the vapor pressure is directly proportional to the mole fraction of the solute. By rearranging the equation, you will get P naught P divided by P2 is equal to X2, or delta P divided by P naught is equal to X2. So this is the lowering, relative lowering of vapor pressure is equal to the mole fraction of the solute, mole fraction of the solute. So this is the third definition of the Rolle's law. Chapter number 10, solutions. Now students, 10.31, causes of lowering in vapor pressure. Causes of lowering in vapor pressure. Causes of lowering in vapor pressure. So students, when you are going to add a non-volatile and non-electrolyte solute in a solvent, the vapor pressure of the solution is going to be decreased. This is called lowering in vapor pressure. This is a 10.31 article and the page number in my book 350. Causes of lowering in vapor pressure. You are seeing the two diagrams here. One contains pure solvent, water or any kind of pure solvent. All they have a same type of the molecules of solvent. So equal rate of evaporation, and you can see without presence of the solute, they have the more vapor pressure because their molecules are more vaporized. But in the case of the solution, when you put the solute particles, they are not going to be ionized, yes, they dissolve, sugar, glucose, urea. They interact with the solvent particles, so they make hindrance to evaporate. So you can see that the solvent particles, they have the less amount of vaporization, so vapor pressure will be decreased. So this is called lowering in vapor pressure. Decreasing the number of surface solvent particles decreases the rate of evaporation of the solvent, as you see in the figure number 2, which decreases the vapor pressure. Thus, the vapor pressure of solution containing non-volatile solutes is always less than the vapor pressure of pure solvent. Then there is a very important thing, colligative properties. Colligative properties of solution. So colligative properties of solution, when we are going to add non-volatile or non-electrolyte solutes, so there is a lowering in vapor pressure, as I told you. Lowering in vapor pressure, elevation of boiling point. The boiling point of solution is going to be increased as compared to pure solvent. Depression of freezing point. The freezing point of the solution is going to be depressed, decreased, and osmotic pressure. So, dear students, lowering of vapor pressure, already I told you, when you are going to add non-volatile or non-electrolyte solute, so escaping tendency of the solvent particle is going to be decreased at the surface of the solvent, so vapor pressure is going to be decreased as you done before. According to the third definition, I told you the relative lowering of vapor pressure, delta P over P naught is equal to x2. Delta P over P naught is equal to x2 as we done before. We have the binary solution of the two components. If the number of mole of one component and number of moles of the two components, solute and solvent, number of moles of one and number of moles of two, then the mole fraction of the one will be is equal to n1 divided by n1 plus n2, and mole fraction of the second one will be is equal to n2 divided by n1 plus n2 like this one. So when you are going to calculate this, there is one thing you have to find, because this is the x2. x2 means mole fraction of solute. x2 mole fraction of solute, so means this one. We are going to consider this one. And 2 over n1 plus n2. There one point please you have to remember. Since for dilute solutions, solute is a very small quantity, the n2 is less than n1. This n2 is less than n1, very less than n1. So that's why this n2 on the denominator side is approximated or make a constant. So that's why x2 will be is equal to n2 over n1. This is going to be constant approximation. Now, after this calculation, you know the number of moles. Number of moles, mass in gram over molar mass. So mass in gram we have to use W1 here, and molar mass is M1. And for the M2 is W2 over M2. These two. So when you are going to insert these two in equation, then this equation can be written as, because this x2 is equal to n2 over, so this is delta P over P naught is equal to n2 over n1. So we are going to write this equation now. When you are putting value of n1 and n2, then the equation you will get delta P over P naught will be is equal to W2 n2 divided by W1 and n1. This is the equation. So when you are going to calculate the value of molar mass of the solute N2, then it will be W2 multiplied by N1 multiplied by P naught divided by W1 multiplied by delta P. So when you are going to calculate the molar mass of the solute, mass of solute, molar mass of solvent, delta P partial pressure of the pure solvent, this is the weight of the solute, and delta P. So these are the formulas you have to calculate. There is an example which is given 10.2. P naught is a 98.6 torr which is given. P is a 68.7 torr. P naught is the vapor pressure of pure solvent. P is the vapor pressure of solution. Delta P is equal to P naught minus P. You will get 11.9 torr, that is the delta P. W2 is a 106.3 grams. W1 is the 863.5 grams, you can see. And compounds, the benzene, the formula is C6H6. So molecular mass of benzene is 78 grams per mole. C6H6. Then put these all values in this formula. You will get the molecular mass of the solute 79.5 grams per mole. 79.5 grams per mole. When you insert all these values in the formula, and you will get the answer. So students, this is the causes of lowering of the vapor pressure, and I told you some derivation here and how to calculate the molecular mass of the solute by using the third definition of the Raoult's law, that lowering of the vapor pressure, lowering of the relative vapor pressure is equal to mole fraction of the solute. P naught P minus divided by P naught, or delta P or P naught is equal to X2. So by using this formula, you have to derive the molecular mass of the solute and numericals, and you have to solve them. Then I told you that when the vapor pressure of the solution is going to be decreased, then boiling point of the solution is going to be increased, elevation of boiling point, and depression of the freezing point takes place. So here is explanation, causes of the boiling point, elevation, and the freezing point. Elevation of boiling point and the depression of the freezing point given here. So there is a one point very important. The boiling point elevation and depression of the freezing point depends upon number of particles. Number of particles present in a solution. So these two factors depend upon number of particles present in solution. Not mass, number of particles. Students, we are going to make the solution 1 molar. 1 molar means 1 mole of the solute dissolved in 1 kilogram of solvent. Molarity. 1 mole of the solute dissolved in 1 kilogram of the solvent. Just like this, you have a urea, 1 molar, 60 grams. 60 grams of urea is equal to 1 mole. Glucose, 180 grams of glucose is equal to 1 mole. Sucrose, 342 grams of the sucrose, also 1 mole. So you learned in the grade 9 the atomic mass, molecular mass, formula mass if expressed in grams is called mole. So molecular mass of urea 60 grams 1 mole. Molecular mass of glucose 180 grams 1 mole. Molecular mass of the sucrose 342 if expressed in gram is equal to 1 mole. All these are the non-electrolyte and non-volatile substances, so they did not going to give the ions in the water, and they are soluble in water. So if I am going to calculate the number of particles, means molecules, if I am going to calculate the number of molecules for all, molecule is equal to moles multiplied by Avogadro's number. So all equal 1 mole, 1 mole, 1 mole and 1 mole. Even their masses are different because of number of atoms. Nature of the number of atoms is different. That's why molecular masses are different, but number of moles same. So that's why molecule is equal to number of moles multiplied by Avogadro's numbers. Means all they have the same particles. All these three components or substances or compounds, they have the same particles. There will be no confusion that if you have three beakers containing 1 kilogram of water as a solvent, and we are going to calculate molarity. So 60 grams will dissolve, 180 grams will dissolve, 342 grams dissolve, 1 mole and particle same. So there is an equal elevation of boiling point and equal depression of the freezing point. If 60 grams dissolve, 180 grams dissolve, 3/4. So this is going to be same elevation of boiling point because they have same number of particles. When they have the same number of particles, their increasing and depression of the boiling point and freezing point respectively will be same. So dear students, if you have a 1 molar solution, these are all 1 molar solutions. So elevation of boiling point is a 0.52 degrees centigrade. If you have a 1 molar boiling point, molar solutions of these 60 grams, 180 grams, 342 grams dissolved in 1 kilogram of the solvent, this is the elevation of boiling point, 0.52 degrees centigrade equally, because these solutions contain equal number of particles. Don't say that 342 dissolve more boiling point, 180 then second number. No, number of particles are same. Number of particles are same, molecules are same. That's why equal increasing of the boiling point. So this is known as a molar boiling point constant. Molar boiling point constant. 0.52 degrees Celsius increasing in the boiling point, elevation of the boiling point is called molar boiling point constant, or we call ebullioscopic constant. Molar boiling point constant. Ebullioscopic constant. Ebullioscopic constant or molar boiling point constant, which is called Kb. Kb, molar boiling point constant or ebullioscopic constant for the water. When you are putting 1 molar solution, so this is going to be depend upon the molarity. more the molarity, more the increasing, less the molarity, less the increasing. So this value I told you. Now students, there is an explanation here in the figure number 10.6. So you are seeing how the boiling point is going to be elevated. Elevation of boiling point. Elevation of boiling point. So this is the x-axis. We have temperature T, and this is the y-axis, and here we use the vapor pressure. So this is the P naught, vapor pressure of pure solvent, vapor pressure of pure solvent, and this is the external pressure. You know that when the vapor pressure of the liquids become equal to the external pressure, the liquid is going to be stored. Boil, we learn the definition of the boiling point. So first of all, you have to calculate the vapor pressure and the temperature boiling point of the pure solvent. Pure solvent. So pure solvent has more vapor pressure. It has more vapor pressure. So this is the vapor pressure of the pure solvent. Vapor pressure of pure solvent. So when I am going to increase the temperature, the vapor pressure is going to be increased. Increasing the temperature, vapor pressure is going to be increased. Increasing temperature, vapor pressure is going to be increased, and here equalization points come. Where the vapor pressure of the solvent is equal to external pressure, the liquid starts to boil. So you have to come here, this point, and this is called a T1. This is called a T1, and this is the B. Like this. So now when you put the solute, its vapor pressure is going to be decreased. Now this is the solution. Vapor pressure is going to be decreased. So when I increase the temperature, the vapor pressure is going to be increased. Increasing temperature, the vapor pressure will increase, and here the equalization points. And because of the vapor pressure is going to be decreased and the boiling point is going to be increased, so you will get boiling point here. This point temperature is 32. So you can see that the boiling point of the solution is greater than that of the pure solvent. This is a pure solvent and this is a solution. This is higher and this is less. That's why delta TB will be equal to T2 minus T1. In your book, wrong written T1 minus no. It's a T2 minus T1. And this is directly proportional to the concentration of the solution. Concentration of solution. That's why delta TB is directly proportional to molarity. More the concentration, more the boiling point. So if I am going to make the constant delta Tp is equal to molar boiling point constant or abelioscopic constant, already I told you. So if molarity is 1, then delta Tb is equal to Kb. The elevation of boiling point means 1 mole of non-volatile and non-electrolyte solute dissolved in 1 kilogram of the solvent. 1 mole, already I told you, give examples. When you dissolve 1 mole of non-volatile or non-electrolyte solute dissolved in 1 kilogram of solvent, this is called molar boiling point constant. Kb, which depends upon the nature of the solvent, not the solute. Dear students, then you have to derive the formula. Here the molarity is the molarity. So molarity is equal to number of moles of solute, means mass in gram of solute. W2, mass in gram of solute, multiply by 1000 because it is in the kilogram, this is in the grams, divided by molecular mass of the solute, multiply by W1, which is the mass of the solvent in kilograms. This is the molarity. So put this value here. So delta P B will be equal to K B multiplied by W2 1000 and 2 multiplied by delta W1. So this is a formula of the delta T. If you want to calculate the elevation of boiling point, this is a constant, you should have this value. This is a constant, you should have this value, you will be able to calculate the delta Tb, or even you can calculate the molecular mass. You are well able to calculate the M2 value. So M2 value will be equal to Kb, which is the adiabatotic constant, multiplied by W2, multiplied by 1000, divided by delta Tb, multiplied by W1. So you will be able to calculate the molecular mass of the solute also. So dear students, here the numerical, you can solve this one according to these formulas. So they are the one apparatus. Then I am going to end Landsberger's method for the calculation of the elevation of boiling point. See the apparatus here down, a graduated inner tube, a hole in its side. So you can see the right side, there is a tube which has a small hole inside. You can see the small hole, and there is a thermometer inserted, and also a bent tube is going to be overhead, and bent tube is going to be added here. The boiling point of it sends the solvent. There is a flask. We put the solvent. We use the capillary tube for the safety pin, then heat it. This capillary tube is going to be evolve the vapors, extra vapors, and boiling solvent is going to boil, and the vapors are going to pass through the small bent tube, and they enters in the boiling flask, which is graduated. The boiling flask which sends the solvent vapors into inner tube through the rose head. There is a rose head. It is going to be hot because there are hot vapors are there, and these vapors are going to be increase the temperature of the solvent and solution and going to be boiled, and you can calculate the boiling point by using a very sensitive thermometer which is called Bachmann's thermometer. Bachmann's thermometer is very sensitive, which has the ability to measure 0.01 Kelvin, 0.01 Kelvin. So you can calculate the T1 by the solvent and T2 for the solution. Then take a difference of these. You will be able to calculate the molecular mass. So here is given the numerical, and you can solve this. So thank you very much. We are going to stop here.